The paper introduces a model-based super-resolution framework, Model SR, which aims to recover high-resolution signals from low-resolution measurements. This framework is locally Lipschitz stable under mild conditions and involves a low-resolution sampling operator GL and a high-resolution sampling operator GH. The super-resolution factor, SRF, is defined as the ratio of the high-resolution sampling points to the low-resolution sampling points. The signal space is defined as an equivalent class, where two signals are considered equivalent if they have the same sampling values. The low and high-resolution signal spaces are denoted as HL and HH, respectively, and a downsampling operator Q is defined to satisfy the commutative diagram in Figure 1. The goal of super-resolution is to find a resolution-enhancing map L that satisfies the condition L hollow bullet GL equals GH. The paper also discusses specific models under Model SR, including the point source model, signals with a finite rate of innovation, and signals with a specific continuous form in the physics domain. A stability estimate is derived for the point source model, showing that exact recovery of point sources from noiseless low-resolution measurements does not require a minimum separation distance condition. The paper is organized into 9 sections, with Section 2 introducing the model-based super-resolution framework, Section 3 focusing on the mathematical theory, and subsequent sections discussing specific models and numerical experiments. Notations used throughout the paper are defined, including the L2 norm, operator norm, Dirac measure, Frechet derivative, and Fourier transform. Here is a combined summary of pages 58 of the research paper. In the context of super-resolution, the authors propose a consistency condition, Condition 1, which states that the low-resolution sampling operator GL must be injective to ensure the well-posedness of the super-resolution problem. This condition implies that the signal profile can be determined from the measurement, and its lack leads to the non-uniqueness of the super-resolution problem. The authors introduce a model-based super-resolution framework, where the signal space omega is regarded as a finite-dimensional manifold embedded in the infinite-dimensional space S, R. A modeling pair, theta, P, is defined, where theta is a compact parameter space and P is a surjective and continuous map from theta to omega. The authors define the intrinsic dimension of the signal space omega as the dimension of the parameter space theta, which satisfies certain local bijection properties. In practice, the exact intrinsic dimension of the signal space may not be available and needs to be estimated. To address this, the authors introduce the concept of compatibility for the case when the dimension of the parameter space is larger than the intrinsic dimension of the signal space. The authors define the low-resolution map PL and high-resolution map PH using the modeling pair, theta, P. The numerical methodology for the super-resolution problem involves 2 steps: estimating the parameter Th by solving a non-convex optimization problem, and obtaining the resolution-enhanced signal by calculating pH, Th. The optimization problem involves minimizing the objective function phi theta equals 1/2 parallel nabla dBPL theta y squared. To ensure uniqueness of the recovered signal, the assumption 2 kiloliters plus 1 greater than dim theta is required. The authors also develop a fundamental mathematical theory under the model-based super-resolution framework, including a stability estimate. The stability estimate is derived using the local property of the low-resolution map and the Lipschitz continuity of its inverse. The authors prove Theorem 3.1, which states that for every theta element of U, there exists Cu greater than 0 such that parallel theta parallel is less than or equal to Cu parallel PL theta place theta parallel. They also provide a corollary, which gives a Lipschitz stability estimate for theta sigma admissible parameters. The research paper discusses the stability and optimization aspects of a resolution-enhancing map, starting with a theorem that establishes a stability estimate for the map. This theorem relies on the Lipschitz constant Cu and the bound for ba nabla dBLDPH, ba nabla d blop, both of which are crucial for understanding the map's behavior. The stability result is then used to analyze 3 concrete signal models, highlighting the relationship between the stability of the resolution-enhancing map and the super-resolution factor, SRF. In the context of super-resolution, the point source model is considered, where signals are generated by n sources in the interval 0, 1, with amplitudes taking values in a closed interval I subset of AI. The model map is defined as p theta equals psi x equals n array summation nj equals 1 theta j 1 delta theta j 2, where theta j 2 represents the position of the point sources, and theta j 1 the corresponding amplitude. The intrinsic dimension of the signal space is 2n. The low and high resolution sampling operators, GL and GH, can be defined by equations 2.2 and 2.3, respectively. Consequently, the noisy low-resolution measurement can be expressed as yk equals gk plus weak equals n array summation nj equals 1 theta j 1 e caret 2 pi I theta j 2k plus weak k equals kl where weak is the noise term with weak less than sigma. We assume that kl is greater than or equal to n. The Rayleigh length of this system is defined as RL equals half a kiloliter. The paper also presents theorem 4.1, which states that for any given theta asterisk operator equals theta asterisk operator 1, theta asterisk operator n, 1, theta asterisk operator 1, 2, theta asterisk operator n, 2, element of theta. Let delta equals 1/2 minp does not equal q, theta asterisk operator p, 2 theta asterisk operator q, 2, and u equals n array product nj equals 1b, theta asterisk operator j, 1, theta asterisk operator j, 1, 2, intersection I times n array product nj equals 1b, theta asterisk operator j, 2, delta. Then, there exists Cu greater than 0 such that for any theta, element of theta, nabla theta, nabla is less than or equal to Cu nabla pl, theta, place, theta, nabla. Further, we have nabla dph nabla 2 op is less than or equal to 2kh plus 1, n plus 4 n pi 2a 2i, 3, kh plus 1, 2kh plus 1, define C, 2. By letting Q equals CuC, we have nabla pH, theta, phosphorus monohydride, theta, nabla is less than or equal to Q nabla PL, theta, place, theta, nabla. As a consequence, if theta element of UBA, theta, sigma, admissible parameter, then nabla pH, theta, phosphorus monohydride, theta asterisk operator, nabla less than 2Q sigma. In the context of signals with a finite rate of innovation, we consider the super-resolution problem focusing on signals generated by derivatives of Diracs. The model map is defined as p theta equals psi x equals r summation display r equals 0 n r summation display j equals 1 theta r j 1 delta r theta r j 2. For the grid omega k equals k, we have gk equals r summation display r equals 0 n r summation display j equals 1 theta r j 1 minus 2 pi I k re minus 2 pi I theta r j 2k. The noisy low-resolution measurement can be expressed as yk equals gk plus weak, where weak is the noise term with weak less than sigma. We assume that kl is greater than or equal to n. The Rayleigh length is defined as RL equals half a kiloliter. Applying theorem 3.1 and corollary 3.2, we have the following stability estimate. For any given theta asterisk operator, let increment r equals 1/2 minp, negation slash equals qdt, theta asterisk operator r, p, 2, theta asterisk operator r, q, 2. We assume that theta asterisk operator r, j, 1, negation slash equals 0, forge equals 1, and r equals 0, r, and increment r greater than 0. Let u equals product text rr equals 0, product text nrj equals 1, parent left igb, theta asterisk operator r, j, 1, theta asterisk operator r, j, 1, 2, intersection I, parent right ig times product text rr equals 0, product text nrj equals 1b, theta asterisk operator r, j, 2, increment r. Then, there exists cu greater than 0 such that for any theta, element of theta, nabla dBl theta minus theta, nabla dBl is less than or equal to cu nabla dBl pl, theta, minus place, theta, nabla dBl. Furthermore, we have nabla dBl dph nabla dBl 2op is less than or equal to kl. Summation display k equals minus klr, summation display r equals 0 nr. 2 pi k, 2r, parent left big 1 plus 4 pi 2 k 2 a 2 I, parent right big define c, 2. By letting q equals cuc, we have nabla dBl ph, theta, minus ph, theta, nabla dBl is less than or equal to q nabla dBl pl, theta, minus place, theta, nabla dBl. As a consequence, if theta element of U is a theta sigma admissible parameter, then nabla dBl ph theta minus ph theta asterisk operator nabla dBl less than 2q sigma. This is a stability estimate for the super-resolution problem in the context of Frey signals. The paper discusses the super-resolution problem for signals with continuous profiles in the physics space, focusing on the stability and resolution enhancement of the proposed numerical scheme. It begins by introducing a theorem that establishes the connection between the physical and data spaces, providing a bound on the difference between the physical and data space solutions. This bound is crucial for understanding the stability of the super-resolution problem. The paper then moves on to discuss the numerical experiments conducted to test the proposed method, including experiments on point source models and signals with a finite rate of innovation, demonstrating stability and resolution enhancement capabilities. The research presented here focuses on enhancing signals in the physics domain using resolution enhancement techniques. Figure 5 showcases the original signals and their enhanced versions, demonstrating the method's effectiveness. A numerical experiment is conducted involving a noiseless signal with monopole, dipole, and quadrupole sources, positioned to have comparable low-resolution signals. The reconstruction results, illustrated in Figure 7, highlight the small absolute position reconstruction error for the quadrupole source, attributed to the sensitivity of the loss function to higher-order poles. The Dirichlet kernel is introduced to visualize the resolution-enhanced signal, which is achieved by convolving it with the derivative of Dirac, resulting in increased resolution. The study also presents the reconstruction of closely positioned point sources in Figure 6 and a box plot of source positions reconstruction error for different types of sources in Figure 7. The research further explores the amplification of signal strength using Dirichlet kernels, crucial for resolving sources in the physics domain. It is demonstrated that different orders of Diracs generate signals of different amplitudes. The experiment results show a stable reconstruction of the source positions, and the extrapolation in the frequency domain results in reliable resolution-enhanced signals. The paper also investigates more complicated signals, specifically linear combinations of components having a specific form. The signal is written as a sum of these components, with each component having different parameters. The experiment considers a signal with 4 components and aims to recover high-frequency data to achieve super-resolution. The signal is visualized on 2 finer grids with step sizes of 1/127th and 1/4095th, respectively. The initial guess of the parameters is obtained by adding or subtracting a constant around 0.07 to the ground truth. The signal-to-noise ratio, SNR, of the experiment is 30.16. The research paper explores the application of a model-based super-resolution framework in the physics domain, focusing on signal profile interpolation and recovery. It presents experiments with varying super-resolution factors to enhance signal resolution, demonstrating improved signal quality with finer grid resolutions. The paper also extends this framework to data completion and deep learning-based super-resolution, highlighting potential for similar structures in other problems. In the data completion section, it illustrates the use of partial and full sampling operators to develop a model-based framework. For deep learning, it draws parallels between the model SR and generative models, emphasizing the importance of learning the map from the latent space to the signal space. The discussion highlights the technical aspects of the methods, including the use of Fourier transforms and the importance of low-frequency data in parameter estimation. The paper develops the theory of the model-based super-resolution framework, presenting a general mathematical theory along with concrete examples and numerical experiments. It shows that under suitable modeling, super-resolution problems enjoy certain stability. The framework's challenging part is the non-convexity nature of the objective function, requiring good initial guesses for gradient descent algorithms. Efficient methods for selecting good initial guesses are left as future work. The model-based framework can be generalized to other problems, offering another perspective on the super-resolution problem and taking a step forward in understanding model-based problems. The paper includes an appendix with a detailed proof of Theorem 3.1, crucial for the stability analysis of the model-based super-resolution framework. The proof involves several steps, including the large distance case, short distance case, and a final step utilizing convexity. The entire framework is designed to provide a deeper understanding of the connection between model-based super-resolution and deep learning, highlighting the importance of efficient initial guess selection for future research. The proof of Theorem 3.4 commences with the solution to equation 2.8, followed by the calculation of nabla phi theta and nabla 2 phi theta. This establishes the positive definiteness of dPl theta, dPl theta, and the existence of a closed neighborhood U theta. The proof then demonstrates the positive definiteness of nabla 2 phi theta for all theta element of U theta, culminating in the definition of nu L. Subsequently, the proof of Theorem 4.1 is presented, focusing on the injectivity of PL, U and dPl, U. The matrix forms of the equations are explained, along with the application of Weyls' theorem. The injectivity of dPl, U is demonstrated through the calculations of partial differential psi, partial differential theta j, 1, k, and partial differential psi, partial differential theta j, 2, k. The paper also discusses the injectivity of matrices related to signal processing and its applications. Confluence-Vandermonde matrices are introduced on page 27, with their properties, specifically their injectivity for any given parameters, being proven by showing that the matrix has full column rank. This is crucial for ensuring that the signals generated by different sources can be uniquely identified. Page 28 further develops this concept, detailing the estimation of a specific matrix's norm and its implications on signal processing. The proof involves calculating the partial derivatives of the signals with respect to the parameters and demonstrating that the resulting matrix has full column rank, making it injective. This injectivity is essential for various applications in signal processing, including source separation and deconvolution. The research delves into the injectivity of the derivative of the probability distribution function, PDF, for a specific class of distributions, establishing the linear independence of certain vectors. This is achieved through a series of equations and identities, leveraging the properties of the distribution's parameters, to demonstrate the full column rank and injectivity of the derivative of the PDF. The proof is divided into 3 steps, focusing on the linear independence of vectors derived from the distribution's parameters, the injectivity of the derivative, and the estimation of the derivative's norm. The research contributes significantly to the understanding of the properties of the derivative of the PDF, particularly in the context of the specified distributions. The mathematical properties of the distribution's parameters and the careful manipulation of equations are crucial in this argument. Furthermore, the study discusses the upper bound of the objective function f for any given theta in the set U, derived using a series of mathematical inequalities, leveraging the convergence of a specific series. This bound is significant as it is independent of kh, ensuring the results are scalable. The research highlights the importance of super-resolution techniques, referencing various works in seismic super-resolution, medical imaging, and radar imaging. It emphasizes the need for stable extrapolation of analytic functions and the role of condition numbers in Vandermonde matrices. The limitations and future work are also discussed, including the need for more efficient algorithms and the exploration of new mathematical frameworks. Overall, the The research provides a comprehensive understanding of the injectivity of the PDF's derivative and the upper bound of the objective function, with significant implications for various applications. The research on pages 33 to 36 focuses on various aspects of super-resolution, including mathematical theories, algorithms, and applications. It begins with the development of novel methods for sparse signal recovery, direction of arrival estimation, and multidimensional super-resolution, establishing theoretical foundations through sparse representations, atomic norm minimization, and Fourier analysis. Experimental results demonstrate the effectiveness of these methods in improving resolution and accuracy in image and signal processing, highlighting the importance of sparsity. The paper then reviews various techniques and methodologies in image super-resolution, dimensionality reduction, and inverse problems on low-dimensional manifolds. It discusses deep learning models, low-dimensional model-based electromagnetic imaging, autoencoders, and inverse problems, addressing issues like ill-posedness and the use of sparse coding. The overview also includes sampling signals with finite rate of innovation and off-the-grid recovery of piecewise constant images from few Fourier samples. The paper serves as a detailed guide to the current state of the art in these fields, highlighting key methodologies, challenges, and future directions.